Before we start doing some practical thing, let me quickly cover once again which platforms we had. Actually, it was release 12. We added F1 instance, but from this slide you can see that we can fit from 1 to actually up to 8+ cores. On Amazon instance, we have 12 cores which run at 62.75 megahertz, and we also had this board which can run at 100 megahertz, and the price range is from 600 up to 7 or 8,000. So you can choose whatever platform you like depending how many cores you want to use. Prototype architecture. There are basically main part which is Ariane core here on the chip. It's actually the same board as you have in front of you. And everything around this is I/O. So first we have DDR controllers over there. So DRAM, it has 2 gigabytes this board and is used as main memory. The second peripheral is SD card in the right upper corner, and it has OS image, and OS basically boots from there. The third peripheral, which is the only one which included in every design, is UART. Basically, it serves as a terminal I/O. It's in the left upper corner. And the fourth peripheral, which is also optional, is Ethernet controller. So actually, the configuration which we will be showing has that controller, and it is connected to the switch, and you will be able to communicate with each other and play Tetris. Okay, now we know architecture. I think we help to configure serial terminal, and if someone hasn't checked that setting in Mac, please check this scroll box so the Linux doesn't crash while booting. And yeah, if you have questions, feel free to ask. And yeah, once again, on Windows, you can find which device is in Device Manager. So now you should connect USBs, which go from the board to your laptops and all see that serial device. It's either COM 3 or 10 on Windows. It will show up STTY something like USB 0 for Linux. And I guess it will be also in dev folder on Mac. So hopefully you were able to identify which port we are going to use. And on Windows or even on Linux, if you're using PuTTY, you should choose your COM and set the speed to 115 to 100. This is baud rate, which the FPGA will be talking to the PC or laptop. And yeah, you need to select also serial, for example, for the PuTTY, or you can just open that dev TTY device using screen in Linux. So while we are doing that, if you have a question, once again, just raise your hand, we will help. But I will cover just 3 main configurations which the tool chain supports. There are actually more options, but for now, I will cover this. So the first one is when you synthesize test into your design. It's basically made so you can be able to see if your design works and be able to run one test without any interface to your host. The second configuration is when you have that SD peripheral along with Ethernet. It's can be used, for example, for these demos. When you flash image on SD card, you can change it and have the same design over time. And the third option is actually designed to be able to run different assembly tests on the bare design. It's helpful, for example, if you change some hardware feature and want to make sure that it works, you can run 1,000 tests from your host on bare metal and see if new design works or not. It's much faster than any simulator. Now let's go to the tools, and two main tools we use for FPGA is the one ProtoSyn, used to generate programming bit files for your design. Also it used to create projects, and recently we added support for generating F1 images. It's actually not bit file, it's design checkpoint, but eventually after Amazon post-processing you will get bit file too. So what ProtoSyn takes is it takes a number of options which specify the board design, it specifies number of cores, type of core, and after that currently we support Vivado toolchain, and it produces the required output. The second tool is named Python Stream, and this is the tool which can be used for those assembly testing. So it basically connects your host machine to FPGA, compiles assembly tests, converts them to the stream, which is understandable by FPGA board, and runs all assembly tests one by one, and providing results, either test passes, fails, or timeouts. This diagram can be a bit scary at first glance, but you should just see three portions here. So the first one is basically saying if we are going to generate a test in the BRAM, it's on-chip memory where you can store tests all of the time. The second part basically says if we are going to create a project, because for example if we already have all the files and we just like changing a bug, we do not want to redo the project and run all IP generators. And the third part of this diagram is if you want to implement. Sometimes you want, for example, just to create a project and add some debugging. And when we added some debugging features, after that we want to implement. So the tool is flexible and provides different entry points to the flow, so you can choose whatever you want to do with your design first. This is a quick help. Actually, I believe it changed over like past releases, but yeah, the main options are the like design, board type, sorry, after that design, the test name if you want to use it, and this is what actually you see when you run ProtoSyn. So you run this command to synthesize Ariane core, and it speeds the configuration. So as Joris mentioned before, we are highly configurable, so you can specify size of L1, L2, number of tiles, and so on. You can pass additional defines, and after that it configures parameters used for the board. For example, yard frequency. It creates a project. It runs FPGA implementation. So it basically follows that diagram which I mentioned on the previous slide. And finally, after implementation, it checks timing. So it basically checks that there are no violations. If there are violations, it would say, you know, there is timing problem. Please take a look at the report. And the runtime depends on the size of the design. So these numbers are presented for one core for the Genesis 2 board, which is on your table, and it takes around 1 hour to generate all IPs. IPs, for example, for Ethernet controller, for memory controller, and yeah, after IPs are generated, it takes around 40 minutes for the whole flow, and for example, for larger designs, it can take several hours. For example, for Amazon, it can take like from 2 to 3 hours. Now, when I cover the tools, I want also quickly to cover the files, so like the logs which you can use to figure out what is going on with the implementation flow. Under OpenPiton folder build, there is specific folder for every board design and every design type. So for example, system, which incorporates cores and IOs. And first, there are like folders which has the logs from the tool. And since we have two steps in the implementation flow, like first project creation and the second one is implementation, this folder has those logs. Now, yeah, let's move to the folder which is Genesis 2 system, and yeah, just know that this XPR file is Vivado file, which you can open manually and modify. If, for example, you add debug cores, there is runs folder, and it has sub-steps of implementation flow, because for FPGA it consists of synthesis and implementation in Vivado terminology, Xilinx. And for example, for implementation, you will see the log from the tool. You will, after the flow is completed, you will have bit file which you actually load on FPGA board, and you will have a lot of reports. For example, this timing report is checked by the tool at the very end to make sure that you met timing and you are good to go. Now, when let's assume we implemented everything, we got bit file. And you can use multiple ways to load that bit file on your FPGA. For example, what we are going to do now is we are going to take the USB, which is already on the table, right? It was, yeah. And please plug it into the upper port. There are two of them. One is like for USB controller. Don't use that. Use upper one. And basically, we have that bit file with the image on the USB stick. And but before we turn it on the board, also make sure that there is SD card in the slot on the right. So there are micro SD cards in like small packs on the tables as well. So those SD cards have OS images and a couple more peripherals which are already connected. So one is UART, which you just connected to your laptop. If you can see the COM port, it means that you are connected. If not, raise the hand. We will help figure out if it's a laptop problem, or sometimes it can be just not plugged fully. And the last peripheral, which I also mentioned earlier, is that Ethernet cable. It should be plugged, so you can go browse internet from FPGA, so you can play Tetris with each other. Well, power is not part of our design. It's part of board interface, so it also should be plugged. If you want to boot Linux on Ariane core. And after you checked everything, just hit that switch and you will see LEDs and you will see this display. And now you should check your terminal. Terminal should have this output. So what it does first is that it copies 32 megabytes from SD card to the main memory, and this is what bootloader does at the very first stage. And after this copy is finished, you will see like 100%. You will see how kernel boots up. So the whole boot process is pretty fast. I believe it's like under 5 minutes. Yeah, after it starts initialization, it will give you prompt. But I think maybe like we'll wait for a couple more minutes until I tell the most secure credentials. Does anyone have like questions meanwhile about like FPGAs and like what actually is there? I can like talk like what is the image or. Let's assume that you are using Xilinx toolchain, so yeah, you compatible. The thing which you need to change is first memory interface, and in our Verilog it's very configurable. So different memories have different physical width. For example, it varies from 32 to 64. So you just take our previous set defines, you change that, and after you regenerate IP for your particular board, you will have memory interface. Also, you probably need to change, well, of course you need to change the part number, right, for a different board. And that should be pretty much. Okay. So yeah, for a new board, it's not complicated because we do not use any special peripherals. accept this USB. So let's assume we have SD card, because like some boards don't have SD cards. For example, Amazon F1 instance, it's like virtual, right, in the cloud, and we do not have access actually, but we still want to have SD card. So what we do is we take the DRAM and we, dedicate one part for SD card. So it's, like kind of additional overhead, but if you take this development board, most of the boards, they have like SD or micro SD. They also have like some kind of external interface, so they have UART for communication. It's kind of default one, which is simple and frequently used for debugging. So mainly it will be one IP core, and you're good to go. The login is root, and there is no password. So after you configured your network interface, just get this DHCP lease. We have like a small DHCP server running, connected through the network switch. Okay, so now hopefully you managed to get network connection. You can like browse your favorite OpenPiton website, or you can ping Google at least. But one more cool thing which you can do is you can play Tetris against each other right now, because you're connected all to the same network. But you need first to figure out who has which IP and port, which the server will be listening to. So for example, you can talk to your like neighbor on the table who has another FPGA and agree which port, and like ask which IP you are using, like here's using. Just like type ifconfig eth0. And after that you should be able to play against each other. I guess everyone now is playing Tetris against each other, or like trying to beat the highest score, right? If not, our members of OpenPiton team will be helping. And meanwhile, I will try to distract you from playing and tell about our OpenPiton on F1 setup. So it's good when you have a board, for example, you like had it in the lab and you decided to port OpenPiton, but for example, you want to put more cores. This Genesis 2 can fit up to two cores, like this is 107, like can fit like up to 4 cores, but let's say you want to put more, right? Let's say like 8 or 16. In that case, you want large FPGA, and large FPGA costs more. And probably it will you can try to use it first on Amazon, or always use Amazon FPGA instances for your research whenever you need. It's very convenient because they provide all development tools. They also give you a license for Vivado, so you do not need to buy any additional tools. And how the design works on Amazon is basically you have 2 parts. One is Amazon shell. On this slide it's on the right, and you have some custom logic which is on the left. In our case, this custom logic is OpenPiton, which has 1 or more cores. Amazon shell has multiple interfaces to that user logic. One of them is XI Lite, which we use to communicate with UART in that custom logic. And basically, instead of having real UART on Amazon, because this board is connected to the host machine in the cloud through PCIe, we read this information via XI Lite from UART and transfer it through PCIe to the host. So we have that kind of virtual UART. The second interface which Amazon provides is the DMA interface, which is used in our case to write data from the host, which is virtually on the right, through the shell to the system on the left. And this is very convenient if, for example, you need an SD card. So these boards, as I mentioned earlier, have micro SD slots, but on Amazon, it's only FPGA with main memory and PCIe interface. There are some more interfaces to connect into other boards, but we do not cover. But you still want to have SD card, and what we did is we just reserved some part of the main memory for the SD card, and we transfer that SD card data through AXI for DMA to the system and emulate SD card in main memory, which is very convenient. Yeah, this is like a generic setup. They're like more detailed you can find in documentation. And synthesizing or making a design for A1 doesn't differ from making design for any other board. Just instead of specifying Genesis 2 for -B option, you specify F1. And all options are the same. So for example, you can even use that infrastructure for running assembly tests on bare metal on Amazon F1 image. So in the same manner, you can check your hardware design changes immediately against your test suite on Amazon, and also see the status of the tests on your screen in the same manner as you had it locally on your table connected to the host machine. Yeah, a bit about runtimes. I think I covered it before. So the synthesis for believe 8 cores is around like 3 hours. Smaller cores take less time. And also there is post-processing step is when it combines the shell and custom logic together. Depending like on the queuing on Amazon, it takes like up to 1.5 hours. It doesn't depend on our design. It's just Amazon latency. And we managed to get 1 core running at up to 125 megahertz on that larger FPGA in the cloud. We also managed to fit 12 cores running at 62.5 megahertz on that FPGA, and it consumes around 70% of lookup tables on FPGA. So we could probably fit more. It just requires more careful placing of your logic on that FPGA. And yeah, it is included in our latest release. So if you're interested, feel free to go and take a look at README. And now we will show how it looks on Amazon. So here we have the same structure, if you notice. So we're like in the Princeton parallel processor in some like tool folder, and we provide the next tool for convenient communication. So we have DMA OS is that program which streams your SD card to main memory. We also provide tools for resetting and kind of disassembling or power of FPGA. So now we have FPGA connected. If we do ls PCI, we see that Amazon listed as device 1042 and 1041. It looks like just memory controller.
So you're logged into
yeah, I'm logged in
to Amazon right now.
Yes, I'm like, this is the F1 instance running in Amazon Cloud, and I just connect to it. I will be SSH'd. And yeah, there are FPGAs connected to it. And what we will do first is we will power off FPGA. After that, we will load an image. So after you generate bit file, Amazon combines, sorry, you generate actually design checkpoint, and Amazon combines it with its own logic and creates a bit file and encrypts it. So the final image is this, like something AGFI and some like key which Amazon is using. And what we are going to do is we're going to load local image to slot number 0, because every instance has 2 slots. We are going to load image to slot 0 using this instance.
And the AGFI here is something that's going to be publicly available, so you'll be able to just go on and grab this exact image. So if you want to do software development, on a 12-core, 8-core, or whatever OpenPiton plus Ariane system, you can do that and just grab our AGFI that's publicly available and run on it directly.
Mm-hmm.
And Amazon to rent one of these images costs about $1.60 US an hour. So it's a little bit pricey, but the board you're renting is like probably a $6,000 board plus a computer, a nice computer.
Yeah, it's actually very good to try it first. So if you do not want to buy like 8,000 board, right, you can spend like some money trying this first, see how it looks, and if you want to use it for longer term, for example, like to run like really long tests or have it like always up, you can buy a physical board, for example. So you can see on this screen that we loaded successfully image. Now we will open an emulated serial port using the program which we provide. So it creates a virtual terminal at this device, and we will connect to it using TIO. Right. Okay, so when it prints connected, it's all good. So now we loaded image, we reset it. So we powered off FPGA, and now we are ready to DMA our SD card to the part of the memory we reserved. It takes really fast, so image is, yeah, so it's already done. You can check that image is, yeah, 2 gigabytes, and it takes like several seconds to DMA, so it's really fast and no overhead. So now we have our FPGA programmed. We have SD card already plugged in, like virtual SD card. And the last thing we need to do is basically reset FPGA, or like it's equal to hitting the power on switch. And yeah, it starts reading from that SD card, and it gives you the same output as a local FPGA. So it copies 32 megabytes from that virtual SD to main memory, which is physically from one part of memory to another part of memory. And yeah, after some time, it will generate the same output. Yes, you can rent multiple instances, and Amazon provides a way to connect up to 8 FPGAs together. But they're using like special interface, and this is work in progress to connect them. Okay, so we have the same prompt as you had on local FPGA, right? And you can actually run cat prod CPU info on your local boards and see how many cores you have. And we can do the same on the cloud and compare a number of cores. So I have 9 cores. But I mean, virtually it looks the same as your local platform. So it's a great tool to try. You don't need physical setup. You have license, you have Amazon servers to run workloads. So you do not, well, you need to rent additional server if you want to run synthesis. But you can also do synthesis locally, what we do. We run like generation of bitstream locally and just send checkpoint to Amazon. It wraps it, and we just program.